Okay, the goal of this lecture is to put a little mathematical formalism around vector spaces and other topic areas concerning eigenvalues and eigenvectors. So this is just covering some definitions and information about vectors and eigenvalues. So the first definition that we want to make is what is a real vector space? Basically, as long as we have some set that includes some elements, we would refer to this as a real vector space or a real linear space. And the elements A, B, and so on are called vectors. And that's independent of their nature. So they can be variables, etc. And as long as within V those elements exist. So given that, there are two algebraic operations that can be performed on elements in this vector space. One is vector addition and the other is scalar multiplication. Vector addition just means that with every pair of vectors A and B within the vector space V, there is a unique vector that's the sum of A and B, and that's denoted by A plus B. And then that's going to follow the following rules, and these are just basic rules that you were probably introduced to in elementary school. Commutativity, which says that A plus B is B plus A, and associativity, which means that the order of the addition of three vectors doesn't matter. We can also define a zero vector where every element is zero, so that if we take some vector A and we add the zero vector, we get A back. And then we can also denote the negative vector A such that a vector A plus its negative is equal to 0. And this is typically done on a term-by-term basis in the vector. Scalar multiplication is multiplication of the vector by a scalar or a constant, and it obeys the distributive and associative properties that are summarized here. Just meaning scalar multiplication distributes across two vectors, or two scalars distribute across a single vector through addition. Associativity meaning that the order of multiplication, if we have two different scalars, is not important. We can multiply one scalar by the vector and then that by the scalar, or we can multiply the two scalars together and then by the vector. Now I should note that vector multiplication is different. Obviously, vector multiplication is a type of matrix multiplication. So this associativity property does not necessarily apply to vectors multiplied by other vectors or matrices multiplied by other matrices. And then finally, for every A and B, there is an identity vector 1 that, when multiplied by A, returns the vector A. The dot product is a special type of vector multiplication. A dotted with B is basically a scalar. Sometimes also this is referred to as the scalar product. So we have basically the dot product of A and B would be the sum of the individual elements A and B. So if A contains A1, A2 through AN, and B contains B1, B2 through BN, then A dotted with B is just the sum of A1, B1, A2, B2, and so on. Obviously, if one of the vectors is of longer length than the other, you can still do a dot product. It's just that the longer vector will be multiplying by 0 for the terms that the shorter vector does not contain. Sometimes the dot product is expressed geometrically. A dot B is the magnitude of A times the magnitude of B times cosine of theta, where theta is the angle between A and B. So in this picture here, the magnitude of A would be the length of A, the magnitude of B would be the length of B, cosine theta would be the cosine of the angle here. Now, you may remember from physics that if we take the magnitude of A times cosine theta, that basically is giving us the projection of A onto the direction with which it forms theta. That can be derived by taking A dot B divided by B. The magnitude A is also known as the Euclidean length. So that would be the square root of A dotted with A. So sometimes A dot B is viewed in this form. And we often talk about projections of one vector onto another vector because it gives us an idea of how close to or far away from orthogonal two vectors are. So if A and B are orthogonal, the angle between them is 90 degrees, which geometrically in 2 dimensions is very easy to visualize. If they lie in the same direction, the angle between them is 0. So your cosine theta will be 0 for orthogonal vectors, meaning the inner product or the dot product is 0. So that's a test for orthogonality that extends beyond a 2-dimensional geometry. So you can have an n-dimensional geometry. At that point, it gets very difficult to visualize what 90 degrees is, but it is very easy to take a dot product and knowing that if it results in 0, you have orthogonal vectors. The inner product space, a real inner product space, basically a real vector space, is called a real inner product space, which is also sometimes referred to as a Hilbert space, if for every pair of vectors A and B in V, there's a real number denoted by A comma B that's referred to as the inner product of A and B, which we've just shown an example of on the previous slide. So this is basically just the mathematical definition or statement that supports what we just looked at. Basically what this says is that there is a linearity property where you can, if you have the sum of two scaled vectors dotted with another vector, then that's the sum of the dots. So this would be inner product of A and C, inner product of B and C, multiplied by this constant. So these systems obey linearity. And then the dot product is independent of whether you do A dot B or B dot A. Once again, it's a geometrical product, so it does obey symmetry. And then finally, for every A in that vector space, the dot product of A with itself is greater than or equal to 0. And it's 0 if and only if the vector itself is 0. So this is referred to as positive definiteness. So if you have a vectors whose inner product is 0, they're called orthogonal. Another definition is the length of the norm of a vector is defined by the square root of the inner product of the vector with itself. A vector that has a norm of 1 is referred to as a unit vector. And the Cauchy-Schwarz inequality is kind of the fundamental theorem or axiom that we get from the inner product, basically saying that the magnitude of the inner product of A and B is less than or equal to the magnitude of A and the magnitude of B. What this really says is that an inner product of one vector is not going to project onto another vector with a length longer than itself. So the projection of one vector onto another will always be equal to or less than the projection of that vector, or than the length of that vector. So from this you can get a couple of additional identities. One is the triangle inequality, which says that the magnitude of the sum of two vectors is less than or equal to the magnitude of the sum of the magnitudes. This just means that two sides of a triangle will always add to something that is greater than the third side. And finally, you can get the parallelogram equality, which basically says that the the sum of two vectors squared plus the difference of two vectors squared is equal to twice the square of each magnitude. So that's the parallelogram equality. Now, what's a linear transformation? Linear transformations are important because a lot of times when we have a space And we have a vector x and a vector y, and we look at it in a space, what we're looking at doesn't necessarily make sense. We may be trying to identify some kind of functional relationship between the spaces. We may be trying to cluster data. We may be trying to do a number of different things. And looking at it in its native space doesn't necessarily make any sense. So one thing that we can then do is we can do a mapping of a vector space, a vector in a vector space X into a vector space Y. And that's denoted by the use of a capital letter. So in this example, we're using capital F. So we have some vector Y in the vector space Y, and it's assigned to a vector X in the vector space X. If that's the case, we call that the image of X under F. So in other words, F is the function that's doing the transformation. X is the function, is the vector that's being transformed, and Y in a different vector space is the transformation. And sometimes it's used without parentheses. Another common use of this is the transformation of a unit vector system. It's pretty commonly done in, say, kinematics. In my lab, we have in the past looked at, we've looked at human movement. So when you do that, you have sort of a base coordinate system, x, y, z. But let's say you're concerned with the movement of the elbow. It could be that the way the elbow moves, and let's say you want to look at how the upper and lower arm are positioned with respect to the elbow, then what you really want is you want the elbow and how it's oriented to be your basic coordinate system. So you can actually map one coordinate system onto another to fit something that doesn't correspond to XYZ. The same thing's done in neuroimaging. If you have somebody in the MRI scanner and you need to talk about a particular organ or a portion of the brain or even some portion of the body that may not be oriented in the same XYZ coordinate system that the scanner is oriented in. So in order to compare, say, 20 people with Alzheimer's disease to 20 people without Alzheimer's disease, if you're looking, say, at some feature in their brain, you might want to remap your coordinate system. So those XYZ unit vectors can be transformed into some x prime, y prime, z prime that's more convenient for the specific thing that you're looking at. So this is just a little bit more about linear mapping. So F is a linear mapping or a linear transformation. If for all vectors v and x in X and scalar c, the transformation of the sum is the sum of the transformations. That's a common definition of a linear transformation. Also, multiplication by a scalar can be done either before or after the transformation and will not affect the final outcome. Linear transformations are reversible. Another common thing is if you're, say, using pattern recognition, sometimes a linear transformation puts your data in a form where you can separate it more clearly into group 1 and group 2, or pattern 1 and pattern 2. And then the nice thing about a linear transformation is then you can undo that and go back into the original space. So this is a little bit like what I was talking about earlier, where you have some space Rn and some space Rm, and you can transform Rn into Rm given some real m by n matrix A that will give you a transformation into that different space. So you can actually have a different number of components in your space. This is pretty common in data reduction. So I think I've talked to you before that in my lab we do EEGs. Our EEG system takes 60 channels of data. A lot of times that's too much data, and so we may want to reduce that data space down to, say, eight whatever's, 8 channels, 8 equivalent channels. And so if we can come up with a linear transformation to take those 64 channels and reduce that into 8 features, that's a linear transformation, and it can be reversible, and that's done through using a matrix. If A is square, then you map R sub n into R sub n. If A is non-singular, then you have an a to the minus 1 that exists. So you can give an inverse transformation. The inverse of a linear transformation is also linear because it's given by a matrix. So this is a fairly common thing to do, to go from one space into another. So this would be more like the analogy where we were talking about if you had a shape that you were trying to compare across several people that didn't necessarily correspond to your XYZ space, you might map that into some new space so that you could run a lot of comparisons from person to person. Composition of linear transforms. If we let x, y, and w be general vector spaces, we're going to let f be a linear transformation that goes from x to y, and g be a linear transformation that goes from w to x. Then we call h the composition of f and g. So h is the composition of f and g. Basically, you can take transformation g, apply transformation f to it. So in other words, here's transformation g, here's transformation f. That would give us h, the resulting composition. So it's like a double transformation. Okay, that concludes the lecture on vector spaces. So the next topic will be to go and talk about matrix eigenvector problems.